Welcome to Math with Malia. Today we're doing Savvas enVision Algebra 1, Topic 6, Lesson 3, Exponential Growth and Decay. After this lesson, you'll be able to use exponential functions to model real-world situations and make predictions. We've got some new vocabulary words: compound interest, decay factor, exponential decay, exponential growth, and growth factor. For the explore and reason, we have Cindy buying a car, and she wants to look at the value of her car over time. She knows that cars depreciate their value. They lose value pretty quickly, actually. So we have insurance actuaries that calculate future value of cars based on depreciation functions, and we have that information here in this table. So here's the car she bought brand new. She drove it off the lot, and she paid $24,000 for it. After 1 year of driving, it is now only worth $19,440. So it has lost $4,560 of value. In another year, it's depreciated or lost value, and now it is worth only $16,560. So then it depreciated $2,880. So it's not a constant rate of depreciation. You can see it loses a lot of value really quickly and then starts to decrease but continues to lose value. Going from year 2 to 3, she lost $2,000. So if we subtract these two, she lost $2,640. And going from year 3 to year 4, she lost $2,250. So she's losing less and less value. It's depreciating at a decreasing rate, okay, but it's still losing value. What kind of function would explain this type of a pattern? So since we're not decreasing at a constant linear rate, let's look to see what maybe a common factor might be. Do we have a consistent number we're multiplying by or dividing by? So let's look at going from year 0 to year 1. What's the percent of decrease? So if I take the second value divided by the previous value, 19,440, divided by 24,000, we can get a decrease. This is 81% of the original value, so it's decreased by 19%. Okay, so it lost 19%. So this is 81% of the original value. Okay, do the same thing for the next year. Take year 2, 16,560, divided by the previous year, 19,440, and this is 85.2% of the original value of the previous value. So now it's lost, about 15%. Okay. Then we'll do the next one, 13,920 divided by the previous value, 16,560. This is 84% of the previous value, so it's lost 16%. And do the last one, 11,670 divided by 13,920. This is 83.8% of the previous value, so it's lost like a little over 16%, 16.2%. So we can see after the first year was a big drop, but then we start hovering right around losing 15 to 16% every year. So it's close to a common factor. So we could say this could be an exponential function. It's losing the same amount over and over again. We're multiplying by the same factor over and over again. Given your answer to part B, what is needed to find the function the actuary is using? Well, we're going to need to find that common ratio, right? To be able to write the equation in exponential form, a times b to the x. So we know the initial value is 24,000, but we're going to need to find that common ratio. Example 1, exponential growth. So we have two types of exponential functions. We have seen exponential growth where it's increasing, and that's what's modeled here with population. The population of Hillville grows at an annual rate of 15%. So it's increasing by 15% every year. It's not adding a certain number. We're increasing by 15% of the previous population. Okay, so how would we write that? Here's our basic formula. Okay, and we need to know the initial value, which here it is, 5,000, so it tells us the initial value here. But then what would be the common ratio? So when we're increasing, we are adding to 100%. Okay, so we're going to write the formula like this. This represents exponential growth. 1 represents 100%, and R is the percent rate of increase. Okay, so what's inside the parentheses is known as the growth factor. So B, our common factor, is going to be called the growth factor to show that we're increasing. Okay, and to find B, we take 1, which is 100%, and then add the percent rate increase. So for instance, this would be 1 plus, and we got to turn the percentage into a decimal. We always turn our percentages into a decimal. So that would be our growth factor. Okay, B would be 100% plus 15% more times or to the X number of years. And if we put that together, you could see it like this, where B is just one number. That's 115%, right? So we're increasing, we're keeping the same population, we're keeping 5,000, we're keeping 100%, and we're adding 15% more. So that's how we'd represent the growth factor. You'll see it written as 2 addends, 1 plus something, or you'll see it just as a sum. But notice, this is greater than 100%. So this is the actual percent of increase, but we write it 1 point percent increase to show that it's added to 100%. Okay, so again, we're increasing, that's why we're adding the growth rate. So R is the growth rate. Everything in the parentheses is called the growth factor. That's what we're multiplying over and over again, remember? A factor is something you multiply to get a bigger number. So the growth factor B is everything inside the parentheses. So make sure you can distinguish those two definitions. Growth rate is R. Growth factor is the sum, 1 plus R. It's what B is. The growth factor is B. So another way you might see it, if B is greater than 1, that means it's exponential growth. Okay, we're increasing, we're going above 100%. So then we would write that. We know our initial value, A, is 5,000. We put that into our formula, and then we add 1 plus 15%, and we get that. And so there's our function. Okay, there's our exponential function. And then we could input any number of years to predict the population in that many years, if it's increasing at this common factor or this rate. So that's the next part. What is the expected population in 5 years? That means our input is 5. We're going to plug that into our formula, and you can just type this exactly like this into your calculator. 5,000 parentheses 1.15 parentheses caret 5. So you do use that little caret for the exponent, and you should be able to do it on your calculator. If not, then do the exponent first. Do 1.15 to the 5th power, and then multiply your answer by 5,000. Okay, we get a decimal, but if we're talking about population, we're going to need to round up because we can't have 0.79 of a person, right? So we'll round up and say it's about 10,057 people. Try it number 1. The population of Valleytown is also 5,000 with an annual increase of 1,000. So every year it increases by 1,000 people. Can the expected population for Valleytown be modeled with an exponential growth function, and explain? So let's think about what that means. Our initial value is 5,000, and then we increase by 1,000 people every year. So what does that mean? Are we multiplying by 1,000, or are we adding 1,000 every year? Well, that means we're adding 1,000 people every year. So if I'm adding over and over again, is that exponential? Nope, that is linear. Okay, we're adding 1,000 each year. So that is a linear function. Has a constant rate of increase. We're not multiplying over and over again. This is also called the common difference. It's not a common ratio. The difference is we're adding 100 or 1,000. Okay, so since it has a common difference, we know this is linear. So here's another type of an exponential function that you will use a lot in the real world. It is called compound interest. So if you remember to pre-algebra, we learned about simple interest. That is just interest paid, the same amount of interest paid on the principal. So you get 3% interest based on how much you put in at the beginning, okay? And you get that same amount every year. So that's linear, okay? This would be just increasing at the same amount, 3% of the initial amount every year. But compound interest is different in that the interest is paid on the principal and on the interest that has already been paid. So really, you're charging your interest based on the previous total, the previous amount. So if you compound interest every year, then you have interest paid on how much money was in the account that previous year. You get charged interest on that. And then you get a new total that is increased. The next year, you'll get interest charged on that new total. So you can increase the amount of interest you earn every year because the percentage is multiplied by a new higher total. So this is the formula for compound interest. You'll want to understand what each part means and how to use it. Okay, it's kind of a complicated formula, but all you need to do is substitute values for these variables in the right place and then do the math. So A represents the amount paid, meaning the amount that's in your account, okay? P represents the principal amount or the initial amount. R is the rate of interest, and you're always going to do it as a decimal, so don't forget you always turn in your percentage into a decimal. N is the number of times per year the interest is compounded, and they should tell you that. If it's compounded annually, or if it's compounded semi-annually, or if it's compounded quarterly, or 4 times a year, or if it's compounded monthly, or 12 times a year, okay? And then T would be the time in years. So it could be quarterly. I'll write these out. Quarterly, it would be 4 times a year. Monthly, it would equal 12 times a year. So again, N is the number of times per year. Annual is just 1 time per year, so then N would be 1. The graph below shows $10 at 5% simple interest and 5% interest compound quarterly. So we're going to compare the two. We know simple interest is linear, so we're starting with the same initial amount. We're starting with $10 we put into the account. Simple interest, we're earning 5% of $10, and that's how much you get every quarter. So this is 4 times a year. So you get 5% added 4 times a year, and you can see the simple interest rate. It's increasing at a linear rate, okay? Compound interest, well, since I'm compounding on a new total every year, that means the first time I calculate the interest, I get 5% on the initial amount, which is $10, okay? But then I have a new total. And the next time, the next quarter, the second quarter, I'm going to calculate my interest based on that new total, that new higher total. So you can see it's going to start to increase and have this curve, so that's going to be exponential. It's exponential growth. We could see that also because in the formula, our input, the number of years, is in the exponent. So we do have an exponential function here. So let's apply this and let's do some calculations. Here we have a certificate of deposit. We deposited $3,000. There's our initial amount. Okay, so that's our principal. The annual interest rate is 8%, so we're going to say R equals 0.08. Remember, turn it into a decimal. The interest is compounded quarterly. That means N is going to equal 4. Okay, we're going to calculate the interest 4 times a year. So we plug those numbers into our formula. Remember, this is exponential growth, so we're going to add it to 1 or add it to 100%. Plug those numbers in, and then we can just simplify. So then we're just going to simplify. 0.08 divided by 4 is 0.02. Add them together. Okay, so here's our basic function for that compound interest. Then it's asking, how much will you have in 5 years? Okay, so then we know T is going to be 5. We're going to just add that into our formula. Okay. And again, you can type this into your calculator just like this, 3,000 parentheses 1.02 parentheses caret 4 times 5. Or if you want to put in caret 20, you know that's what that is. Okay, so you're doing 1.02 to the 20. And then if you do that first, that's fine. Then you can multiply it by 3,000. So at the end of 5 years, the value of your CD or certificate of deposit will be $4,457.84, okay, because we'll round. Part B, will Kimberly's CD earn more money if her interest is compounded annually rather than quarterly? So now we're going to compare. We already did quarterly, where n equals 4. What about if n equals 1? So now we're just going to compare if n equals 1. So here's annual over here, and that means we're just dividing the interest rate, 0.08 divided by 1, so it stays. So here's our new formula, simplified, okay, versus that formula for quarterly, okay. It looks like it's only increasing by 2%, but then we also have a multiple of 4 in our exponent, so that's going to change. Our exponent's going to change. So if we distribute that 4, if we do reverse power to a power property, really this is 1.02 to the 4th raised to the t. So what is 1.02 to the 4th? Well, it's this number, and that is greater than 1.08. So you could just compare the two formulas. You could also plug in a number for t and see which one is higher after so many years. But you can see, since we did the power to a power property, then the actual growth factor is 1.08243116. It's greater than 1.08. So technically, she's earning, like, if that's 100% plus 0.0824, that's like about an 8.24% interest rate versus just an 8% interest rate. So this is good advice. The more you can get it compounded, the more frequently it compounds, the more money you will earn. Try it number 2. What will be the difference after 15 years if the interest is compounded semi-annually rather than quarterly? So semi-annual, now n equals 2. Okay, and we know t is going to equal 15. So we're going to have to do these two calculations. Okay, so p is still 3,000. The interest rate is still 8%. Okay, and I'm going to compare quarterly again. And we're going to look at 15 years. So I'll do quarterly first. So if we plug this into our formula, a equals 3,000 times 1 plus 0.08 divided by 4 to the t, okay, or to the, 4 times 15. Don't forget to multiply by n. Okay, and we can do our calculations. So if I type in 3,000 times 1.02 to the 15 times 4 is 60, so to the 60, then after 15 years, we will get $9,843.09. Okay, let's do semi-annually. So the same numbers now, except n is going to equal 2. So let's plug that in. The amount paid is the principal times 1.1 plus interest rate divided by the number of times is 2 to the 15. Now it's going to be times 2. Okay, and I can do the math. So now it's going to be 1.04, so 3,000 times 1.04, because 0.08 divided by 2 is 0.04, to the, my exponent will be 30, 15 times 2 is 30, and the amount paid after 15 years would be $9,730.19. So which one pays more? Well, again, the more frequently you compound, the more money you'll make. Part B, a CD earns 4% annual interest compounded monthly. What is the equivalent annual interest rate? So we're just trying to simplify this. So we don't know the principal. We just know the interest rate and the amount it's compounded every year. Okay, so the principal times 1 plus the interest rate is 4%, so 0.04, divided by it's compounded monthly, so that means it's compounded 12 times to the 12 to the t. Okay, and we just need to simplify this. That's all they're wanting us to do, is just simplify the growth factor. So p to the 0.04 divided by 12 is going to be 0.0033 to the 12t. And then remember, we can apply the property to power to a power property, and so then that's 1.0033 to the 12 to the 12 to the t, and I'm running out. So this becomes p times 1.0407, because if I did 1.0033 to the 12, I get 1.0407. So what's the annual interest rate? Again, how much did we add to 100%? We added 4.07%. So annual interest was only 4%, but if we compound it monthly, it's slightly more. You earn a little bit more interest. Example 3, another application, but now we're going to look at exponential decay, similar to the car's value depreciating. A video is labeled a fan favorite if it receives at least 1,000 views per day. Amelia posts a video that gets 8,192 views on the first day. The number of views decreases, so now we're losing, okay, we're decreasing by the same percentage every time. It decreases by 25% each day after that. In how many days will the video stop being a fan favorite, or it gets below 1,000? Okay, so after 1 day, it's decreased by 25%. So you can just do 25% of the previous day. So 25% of 8,192 is 6,144. Then you do 25,000, because we're multiplying by 0.25. 6,144 times 0.25 would be 4,608. One more time, 4,608 times 0.25 is 3,456. So we can keep doing that to figure out how many days it takes to get to or below 1,000. Okay, this is modeling exponential decay. So notice our growth factor is now called a decay factor because we're losing. We are subtracting 25% from 100. Okay, each time we're subtracting 25%. So it is called a decay factor. We're subtracting from 1. Otherwise, everything else is the same. You could also think of it like this. B, or that common ratio, the growth factor, is a fraction. It's in between 0 and 1. It's not negative. Okay, don't get confused. It's not negative, but it is less than 1. Okay, meaning everything in the parentheses is less than 1. Because remember, everything in the parentheses just represents B, or the common ratio. So you might see it written as 1 minus, like we could write it as 1 minus 0.25 for this case. You could also, what is 1 minus 0.25? You could also see it just written as 0.75. So 0.75, that's 75% of the original amount we have decreased. So you might see it either way. Make sure you're careful of whether it's exponential growth or decay. So we can plug these numbers into our formula. A, the initial value is 8,192. We know the growth factor is going to be 0.75, okay, because we're losing 25%. We're subtracting 25% from 100 over and over again. So here's our formula. And we just need to figure out when this is less than 1. So we can plug this into our calculator to find when this equation is less than 1,000. Okay, there is a way to solve this, but you'll learn that way in Algebra 2. You need logarithms to do this. But let's get on our graphing calculator, and you can type in this function and then use the list feature. So on our graphing calculator, we're going to type in our function into y equals. Again, make sure your plots are off, and we're going to type in that function, 8,192, parentheses, 0.75, parentheses, to the, so caret, and then type your x. But let's use our table feature. So second table, here are our x values and here are our y values, and we're just going to scroll down our y values to see when it goes below 1,000. So there we go. Day 5, it's still good. Day 6, still good. Day 7, good. Okay, after day 7, we get below 1,000. Try it number 3. Suppose the number of views decreases by 20% per day, and how many days will the number be less than 1,000? So let's see how that changes our function formula. F of x equals, what's the initial value? Still the same, 8,192, but now it's decreasing by 20%. Okay, so this becomes 8,192 times 0.08 raised to the x. So let's type that into our calculator and see how many days it takes to be below 1,000. Going back to y equals on our graphing calculator, the only thing we need to change is inside the parentheses, so this just needs to say 80. And let's just go straight to our table. So second graph, and look at our y values. Now it's not until day 10 that it gets below 1,000. Which makes sense. It's decreasing at a slower rate. Example 4, another application problem. So anytime you're dealing with population, either population growth or population decay, losing population, you're going to be talking about exponential functions. Okay, so these are used a lot in the real world, especially in science, biology. The number of pica in a region is decreasing. Look at these cute little rodents. How does the decrease in pica population for years 1 to 5 compare to the population for years 6 to 10? So we're going to look at two different intervals. The interval from 1 to 5, where our input is from 1 to 5, and then the interval where our input is from 6 to 10. Okay, let's see what the graphic tells us. The initial population is 144. It's decreasing by 8% each year. So we know R is 0.08. and we know A is 144. It's decreasing, so we know we're going to be doing 1 minus R to the x, okay? It's going to be a decay factor. So let's plug all these numbers into our formula. A replaced with 144, 1 minus 0.08 becomes 0.92. So here's our function. And now we're going to apply each of those intervals to that function, okay? So we can just look at the endpoints, the beginning and the end of that function, of that interval. So if we do f of 1 for the first time, and then f of 5 is the other input, the endpoint of that interval. And we just plug that into our formula. Okay, so f of 1, if we type it in, 144 times 0.92 to the 1, okay, and then do the same thing for f of 5 for x equals 5. Now we're going to find the rate of change. Rate of change is the same as the slope, so we're just calculating slope. Remember, slope is the change in y over change of x. So the difference in the y values, or the outputs, divided by the difference in the inputs. So our outputs are 95 and 132, so we're going to find the difference. 95 minus 132 over the difference in the inputs. So this is the difference in outputs over the difference in inputs. And we get a decrease. Again, that makes sense. It should be negative because we are losing population. Our rate of change is negative 9.25. Let's look at the other interval. Now we're doing from 6 to 10, so those are our inputs. We're going to do f of 6, that's our first input. We get about 87 when we plug in 6 for x. And then we're going to plug in f of 10, where x equals 10. That's the other endpoint of our interval, and we get about 63. Do the same thing. You're going to calculate the change in f of x over the change in the input to calculate the slope, or the average rate of change. 63 minus 87, 10 minus 6. So make sure you're using the same point, the second point minus the first point, in both cases for output and input. We get negative 24 divided by 4, which is negative 6. So our average rate of change for the second interval later on, more years down the road, it's not changing as much. It's not as steep. If you were to think about a graph, negative 9.25 is going to be pretty steep. Negative 6 is going to be not as steep. So this makes sense. If I draw a graph of exponential decay, you can see that it decreases very quickly in the beginning. So that's a steep slope at the beginning. But later on, it's not decreasing by as much. So it has not as steep as a slope. And then eventually it starts to even out. and be even less and less and closer to a slope of 0. So our rate of change is slowing down. We're still decreasing, but we're decreasing at a decreasing rate. So don't forget your slope formula. You should know that from pre-algebra. It's always the change in y, or the difference in y, over the difference in x. Try it number 4. How would the average rate of change over the same intervals be affected if the population increased at a rate of 8%? So now we're talking about exponential growth. We're going to have a growth factor, something greater than 1 now inside the parentheses. So we're going to be doing the initial value times 1 plus my growth rate, which is 0.08 to the x. Okay, so let's see. My initial value was 144 times 1.08 to the x. How would the average rate of change for the same interval? So going from 1 to 5, we're going to do f of 1 and f of 5 for our new calculation. F of 1 is going to be about 155.52, and f of 5, if you just go up and add a caret to that, to the 5th power, this is going to be about 211.58. Now we're going to find our rate of change. So 211.58 minus 155.52, and the difference is 5 minus 1. And we're going to get approximately 14. I'm rounding because I have population, so I can't have a decimal of a pica. So for the first interval, we're decreasing, the average rate of change is 14 pica. And for the next interval, 6 to 10. Remember, we're going to use these endpoints, so we're going to evaluate f of 6 and f of 10. Okay, so f of 6. Now I just type in my exponent is going to be 6 instead of 5. And that is approximately 228.51. And then one more time, we're going to just change the exponent to be 10. And this is going to be approximately 310 and 89 to find the rate of change. Again, that's finding the slope. So 310, I won't write the decimals, minus 228.51. And then we're going to do 10 minus 6. This is going to be approximately 20.59 or 20.6. We can see, comparing those rates of change, we're increasing. We're increasing at a faster rate. Does that make sense? If we're showing exponential growth, we're increasing faster and faster. So then if I draw those slopes again, here the slope is not as steep, and then the slope is going to get steeper as I continue on. So yes, it's going to be increasing at a faster rate. Example 5, exponential growth and decay. So now we're going to be comparing a decay factor with a growth factor, okay? Two different types of functions, both exponential. Rich is comparing the cost of maintaining his car to the depreciation value of the car. So remember, depreciation value, that's our decay. But maintaining your car, the older your car gets, the more it's going to cost to maintain it. So then this will be our growth, okay? So we're going to have growth here and decay with the depreciation. So looking at our depreciation function, the initial value is $20,000. You can see that in our graph, it's giving us the cost in thousands, so we're going to ignore 3 zeros. We're going to ignore the thousands. It's decreasing by 15% per year. So remember, if it's a decay factor, we're subtracting from 100%, so it would be 1 minus 0.15. So our depreciation function can be represented like this, 20 times 0.85, which is 1 minus 0.15 to the x. And you can see it's represented by that blue graph. It's our decreasing exponential decay. For the cost of maintenance, we have different numbers. The initial cost is $500, okay? And so 500 is half of 1,000. So that's how we get there, because we got to divide it by 1,000. So our decimal moves over 3 places. Okay, so that's why that equals 0.5. And it's increasing by 28% per year. So the cost increases. This is our exponential growth. And so since it's growth, we're going to be adding to 100%. So our growth factor will be 1 plus 0.28, which is 1.28. So here's our function for maintenance, our increasing or our exponential growth. You can see that one is increasing. So we can solve by graphing. We can put these two functions into our graphing calculator and find the point of intersection. Let's do that. On your graphing calculator, we're just going to go to our y equals and type in those two functions. So the blue line was our decay function. So let's type that in 20 parentheses 0.85 caret x. So there's our decay function, and our red line was our growth function. This will be 0.5 parentheses 1.28. We're adding to 100% caret x. Okay, let's see if we can graph those. All right, we can see it. You can see where they intersect. We're trying to look where the cost and the depreciation value are the same. We're looking for the point of intersection. So let's calculate. Go to second, trace, and you can see the option number 5 is intersect. And it's going to ask you which one is your first curve. Yes, that is my first curve. The blue line is my first curve. The second curve, is this the second line? Yes, that's my second equation. Hit enter. Where's your guess? So then you can move your cursor over to about where it's going to be. It's about there. Hit enter, and it should give you the coordinates for that point of intersection. You can see here on the bottom, 9.01, comma 4.62. There's our point of intersection. So that means after 9 years, x is number of years, after 9 years, it'll cost about 4.62. Remember, that's thousands though, so multiply that by 1,000, about $4,620 it will be to maintain, and it will also be the depreciation value. Try it number 5, explain how to use tables on a graphing calculator to answer this question. So we already have the functions into our graphing calculator. So let's go and use the table feature. So again, there's our functions in the graphing calculator. So instead of using the graph like we did on our other example, let's go to second, graph, to get to our table feature. I didn't hit second. And there we have the input values. These are the number of years. X is the number of years. Y1, these are the outputs or the cost or the depreciation value. And the red Y2s, the red output values, that's the cost of maintenance. So we can just compare these two columns. When are they going to be about the same? Look, whoops. When are they going to be about the same? Right here. At 9 years, they are pretty close. We can see that they're about the same at 9 years. So you've got 2 ways to do it. Sometimes if you can't see the graph on your window, the table feature is a good option to use. We made it to the concept summary for exponential growth and decay. We saw a lot of ways that we use these functions in the real world. So make sure you understand these formulas. And if you have a growth factor, b is going to be greater than 1. If it's a decay factor, b is going to be less than 1, but greater than 0. And you'll want to understand how to use the compound interest formula, what each of those variables represent. Okay, you'll need to know where to put the values given. Here are some examples, and here are some graphs. If you have any questions, put them in the comments. Make sure to like and subscribe, and come back for lesson 5.